So let me introduce you to Christian Buck from Technical University of Munich. Please go ahead.
Yeah, thank you very much, and thanks for the chance to present our results here. So this is some ongoing PhD work of these three people here highlighted in red. It's Carolina Luthi, who works with NV centers. Franz Vilsmeier works on caustic spinwave beams, and Christian, among other things, works on chirping spinwave beams. And I would also like to thank Christian Degen for setting the stage here. So he was interested in, among other things, static magnetic properties, and we are interested in dynamic magnetic properties. So we would like to have a method that allows us to investigate spin waves or the excitation of magnetic systems with high temporal resolution, meaning going down to, say, a picosecond or so, and also with high spatial resolution. So typically we work at 250 nanometer resolution in the lab, but we can go to big facilities, synchrotrons, and get a spatial resolution down to 50 nanometers, but there we're somewhat limited in the frequency resolution. So I will give some examples of high-resolution spinwave imaging, and the reason why we're now interested in NV center imaging is, of course, you have this superior spatial resolution, at least for static imaging so far, but also there's a way to image spin waves, and I will give an example in the end. Okay, maybe a technological reason why people are interested in this. You might have heard of the field of magnonics, where we want to use spin waves as computing devices, logic devices. And one key element is to reduce the wavelength of spin waves. So we want to go down in wavelength while staying at high frequencies. So say frequencies around 20 gigahertz, but wavelengths much below 1 micrometer. And there are several ways of doing this. Some of them are borrowed from optics, actually. Some of them are just basic magnetic recipes. And we're also working a bit in this direction. You can also use magnonics to steer spin waves, and I will also give an example why this might be interesting in the context of NV center microscopy. Actually, this mic sounds a bit strange. Okay, so there are various ways. Maybe I'll just go somewhere else to do this. Now, I'm not particularly interested in all these technological aspects. I'm more interested in some fundamental properties of spin waves. So we would like to see some optics effects, Gauss-Hähnchen shift, for example. We are interested in a Magnon-Hall effect. You might know that there are Hall effects for almost everything, topological Hall effects. And we are interested in a Hall effect that is actually predicted for spin waves but hasn't been observed properly yet. And also we're interested in topological magnons in some specific materials. And for all these questions, we need high resolution imaging. I will show you a very simple example as a starter so you get acquainted with what spin waves are. And the example is that we looked at Snell's law for spin waves. It's something very simple. You know this from optics. You know that if you have a wave that impinges onto an interface here, that the refraction and reflection is dominated by the tangential component of the K vector at this interface here. So you have these two materials here with different refractive index, and you know that this is the solution for Snell's law. And in optics, you know that omega is C over n times k. Now for spin waves, and this leads to Snell's law, and you will actually see a reflected wave and a refracted wave, and you know these angles are the same in optics, and then you have a refracted angle, theta 2. Now for spin waves, this is different because we don't have this very simple dispersion relation. So spin waves do not have an isotropic dispersion relation, in particular if you go to thin films, and this is what we're interested in. So in thin films, we have magnetic excitations, the magnons. You can see them depicted here, and these are the eigenmodes of the system. And the dynamics of the magnetization is described by the Landau-Lifshitz equation. And what enters here in this spinning top equation, if you want, is the effective magnetic field. And this field can be quite complicated. You can have exchange contributions, you can have higher order exchange contributions, anisotropies, and so forth. And particularly, you can have also the dipolar energy. Now, the dipolar energy, as you know, is anisotropic. So it makes a difference if you put spins along each other or side to side. And this also holds for the dynamic dipolar fields that you get for the precessing magnetization. So that means that this thing already is anisotropic. And then, of course, the spins don't precess forever, but there is a damping mechanism, and the simplest form to write this damping mechanism is in this so-called Landau-Lifshitz-Gilbert term, where alpha tells you how strongly damped such a system is. Okay, so if you now calculate the dispersion relation for spin waves in thin films, it actually looks like this. So here's frequency, here's k vector at a fixed thickness, and you can see that there are two different branches that I picked out here. One of them is the so-called Damon-Eschbach branch, where the spin wave propagation direction k and the magnetization, the static magnetization, are perpendicular to each other. While if you put them collinear, then you get this so-called magnetostatic backward volume mode, and for all other angles, you fill up the spin wave bands here. So this one is a bit peculiar. It's a surface wave, which means that it's mostly located on one side of the sample if the wave travels in one direction, and it's mostly located at the other side of the sample if it travels the other direction. And this is important if you want later to do spin wave imaging using NVs. So we have these different dispersion relations, and now you can see, if you calculate the dispersion relation for spin waves, that you can actually tune the dispersion relation simply by changing saturation magnetization, so changing the material if you want, but also by changing the thickness here. And if you look at the dispersion, they look like this. So this is light, it's isotropic, and this is now the dispersion relation for spin waves in the XY plane. I'm omitting actually the third direction here. So again, for light, this would look like this. But now, for spin waves, we have to take into account all these angles differently. So now we have angle for the incoming wave vector, for the reflected wave vector, for the refracted wave vector. They're all different. And you also need to pay attention in which direction you apply the magnetic field, because that influences your dispersion relation. So it's crystal clear that if you excite a spin wave here, it follows some branch on the dispersion relation, but if it's refracted, it actually travels on a different branch of the dispersion relation, because the dispersion is not isotropic. Okay, and we can tune the medium by changing the thickness. So now we all just take the same material, we change the thickness, that changes the dispersion relation. So you can do this like this. We fabricate this microwave antenna. We place them onto a sample that has a step-in thickness, so it's a permalloy film which has about 1 Tesla saturation magnetization. Its thickness here is 60 nanometers, and then it travels into a region where the magnetization is the same, but the thickness is reduced to 30 nanometers. And you can do this for different directions, so you just change the angle by fabricating different samples, and the magnetic field in our case is always applied along the coplanar waveguide, which means that we start off in the Damon-Eschbach geometry. And then the method of choice that actually, I don't really care about the method. I just want to investigate the dynamic magnetization with high resolution and quickly. We typically take movies, which means that one image should not take much longer than 20 minutes or so. So I'm not so interested in measuring something over the weekend. And the method of choice that we use is time-resolved Kerr microscopy, where we just have a laser source as a clock. We shine this on the sample. We've doubled the frequency just for resolution issues. And then we measure the rotation of the magnetization in an optical bridge here. And we excite the system with microwaves that are synchronized to the repetition rate of the laser, so we always probe the magnetization at the same phase. We do this for 2 phases, then we get the full information, and we can shift the phase by putting some electronics in here. And you can do this in different geometries, but what we measure is always the perpendicular component of the magnetization. of the dynamic magnetization. Now, in contrast to static imaging, where you go from one domain to the other and you have a full change of the magnetization, we actually image the dynamic component of the magnetization, which is maybe an excursion of 2 degrees out of the plane. So it's a tiny component. And then we do this, as I said, stroboscopically. We can also do line scans and form images, and this is a typical image, so taking such an image takes about half an hour or so. So we have the coplanar waveguide here. The spin waves are excited in this direction. It's actually a confined structure here, so you see some effects from the edges. And then you see the phase fronts of the spin waves traveling out. And here you see a particular point here where you have some strange patterns, which I will come back to later. Okay, now if you do this experiment, essentially this is what you do. You take images as a function of a frequency, for example, or as a function of magnetic field, and we always do various phases so we get the full information. And you can see, in fact, you see a reduction of the wavelength. What we can deduce now are all these k vectors, and indeed you also see the reflected wave vector. If you look at the ridge of one of these wavefronts, you can see there's a slight modulation here. You can fit this, you see the modulation here. You can extract all these wave vectors for different frequencies and different magnetic fields, and then in the end you extract k and the angle for all these different series. One thing that is particular actually is that you see a boost of signal amplitude. If you go here to the edge, you can see that the signal is much larger after it travels through this interface, and this is actually something that we also use to boost signal amplitude. It's clear because your magnetic excitation is coming from the thicker film, but the magnetization is reduced in total in the thinner film, so the angle has to get a bit larger. Okay, now we can compare Snell's law in optics with Snell's law in spin waves. You see it's different. That's because of this dispersion relation. And in particular, you can see that we can now go to very high k vectors, which means that we're also reaching the limit of our resolution. Okay, so we have an efficient means of steering spin waves. We can boost the signal amplitude, and I'm not sure how it works. So this would be a movie that we typically take. So you ramp magnetic field, you can see all these spin waves, you can see how they travel through the interface. At some point it becomes prominent. Before that we cannot image because we don't have the resolution. And this takes maybe a day. And this is where we would like to go with a different method. Okay, I show you one other example, which is a reflection. I showed you refraction just now. Now I show you reflection. And this is something actually quite difficult. It's the so-called Gauss-Hähnchen shift. So what you see here is you have this coplanar waveguide again, and now we just have a physical edge here. So the spin wave travels out and then gets reflected at this physical edge. So it comes in like this, goes reflected here. Now, as I said, in this geometry, these spin waves have this surface wave character. So they travel on one side, and when they reflect, they come back on the other side. And you have to take this into account when you do this imaging. So that's why it's drawn like this, so it actually goes around the corner and travels here. Now, the Gauss-Hähnchen effect tells you that there is a phase shift between the incoming and the outcoming wave. And this is what we like to detect for spin waves. So the principle is here, you have a reflection experiment, and the actual reflection takes place at a virtual interface that is slightly behind the real surface. So it has something to do with the evanescent wave going into this medium. And there are some proposals for spin waves. You need to make some spin wave beams, go to very short wavelength, and then measure this jump here. There are other proposals that we think are actually more interesting. Here, what has been proposed is that you also see a sideways shift because of the Magnon-Hall effect. And this is actually what we're after. It's actually quite difficult because also it requires perpendicular magnetic field to get the particular band structure where this Magnon-Hall effect should be detectable. And we will try to detect the Gauss-Hähnchen shift not with a spin wave beam, but with a plane wave coming into this onto this edge here. So again, these are the waves that go in, and you see some modulation because the reflected waves superimpose what we measure. And now you need to extract what happens at this interface here, and you can see this is actually quite difficult. So this is the full movie again, and now we want to see, can we detect a phase shift here? And yes, we can detect a phase shift here, but where is it coming from? So now you see that the edge is actually not aligned with the magnetic field. So there's also some problems concerning the dipolar fields at the edges. We also have to consider that the reflected wave is traveling on the other surface, and this makes actually this analysis quite difficult. We nevertheless think that we detected this, but it would be nice to have much higher resolution to see what's actually going on at this edge here. Now, one other thing to do this is to use spinwave beams. And spinwave beams are often, in magnetism, we call them magnetic caustics. And you can see a caustic here. And you can see a caustic even nicer here. You see this particularly well in the evening. And you see that there is a high intensity here. So we have many wave fronts, and if these wave fronts have the same group velocity, the amplitude in a particular point can be increased because you form a caustic wave. And we looked at caustics in various geometries, so these are different coplanar waveguides with different notches and different characteristics, and then you image spin waves at a function of magnetic field or frequency, and you can see at some points you can maybe see some caustics, maybe not, and we don't really know if these are interference patterns or caustics. So here's another example where we have a notch here. You can see when you ramp the field, the spin wave properties vary, but you can also see that they're not very well focused, they're not really caustics. Okay, so how to design a proper caustic? So let's go back to this anisotropic dispersion relation. And now I take a slice here at a particular frequency. That's an isofrequency plane. And just remember that this branch is this backward volume branch, the orange one here, and this branch is the Damon-Eschbach one, is the one here. And we have access to this region with our microscope. And if you take a slice here now, then this would look like this. So this is Kx now, this is Ky, magnetic field, for example, in this direction. This would be the backward volume, and this one would be the Damon-Eschbach geometry. Now, to make a caustic, you want to have the group velocity pointing in the same direction, so you need to go on, this is now a quarter of this contour, you need to go to points on the dispersion relation where in the vicinity the group velocity points in the same direction. And you can see these points here. This is where the dispersion becomes flat, and you can see in the vicinity of these marked points, the group velocity points along the same direction, so these waves should add up and should lead to a caustic beam forming. And you can actually model this. We have developed an analytical model now to describe this. Now, this has been observed before. This is a BLS experiment from some years ago. Here, actually, it's not so clear if these are true caustics, but probably they are. And here you do this by making a microscopic or macroscopic sample. Actually, it's a large film with an opening into a larger magnetic material. We do this a little bit differently. We do antenna structures that are shaped like this, so we can run high frequency through this antenna. We have an antenna that is bent here, and we radiate spin waves actually from everywhere, but selecting the proper magnetic field in amplitude, direction, and k-vector, we can create caustics. So one example, so this is the tip of the antenna, this is a topography image, and this is what we calculate for particular parameters, so frequency, magnetic field, and this is what you actually observe. We don't really understand why it's a bit slanted, but this probably has something to do with the geometry. So you can actually design these spin waves. They're now going really in one direction, and nothing happens in these regions. You can do this at different frequencies. You see there's the antenna again, you see the caustic coming out, and now we actually have an interface here. You can see this by the slight change in color. And what we want to see is if we now get this lateral jump, which would be related in this case to Gauss-Hähnchen. If we rotate the magnetic field in a different direction, it could be Magnon-Hall effect. It's not very clear here So we worked on this a little bit more, but before that, we can also steer these caustics by just changing the magnetic field slightly. So here you see, again, this is the contour line of this isofrequency curve. These are the incoming and reflected waves at this interface, and this red one is the magnetic field direction. Oops. And actually this should rotate. What you see essentially is if you rotate the magnetic field, that you can steer these spin waves into different directions. You can see this maybe even better here. So here we have 3 different cases. We can steer the spin wave. You can see this one actually travels back slightly. This one is basically reflected perpendicular to the border, and this one travels forward slightly. Now this wasn't enough, so we thought, why not build such kind of a resonator? So now we have the antenna here. We make 2 slits here, so the magnetic material is in between. We steer the caustic into this resonator, and indeed you can see that it actually bounces back and forth. And if you do some image manipulation, let's say, then you can make this clearer. And now we're hoping to see if we can actually find this Magnon-Hall effect. Now there's something very interesting to this, because now you can steer a spin wave to a particular position. And you could put an NV center at a particular position, and you can steer it on and off from this position. That's one thing. The other thing what you can do is you don't need to apply continuous microwaves to direct the spin wave beam. You could also put in chirped microwave pulses into these antenna. So you would have pulses going along these lines, and you want to chirp them because you want to overcompensate the dispersion in the magnetic material, so to make them sharp at a certain position. So assume you have an NV center here, you want to have a sharp spin wave beam there, so you can send in a chirp beam where you know that after traveling, let's say 250 micron, you actually get a sharp spin wave beam at a certain location. And this is something that we're actually very interested in. Okay, so now this was all spin waves observed with time-resolved curve microscopy. Now you see, what we want is something that is much better than 250 nanometer resolution and should be in the correct frequency range. So let's say right now we can do between 1 and let's say 50, but let's assume we can go to 20. That would already be fine. And to do this, we use now NV centers, or we play around with NV centers to see how far we can actually go. I guess I don't need to explain this anymore. This was done perfectly by Christian. So we have this NV center. We can read out magnetic resonance optically, and you can mix the spin states here by applying microwaves and additional magnetic fields if you want. And we have these 2 branches that we see later. This, the omega plus is the upper one, omega minus is the lower one. And you can see that you, in fact, because you have 4 different axes, you actually have 8 lines that you typically observe in an experiment. So it's actually quite difficult for us when we want to set a certain magnetic field in a certain direction, but we should also maximize the NV contrast. So this has to somehow work together. Anyways, this is solvable. And what you see here is NV center in a chip with narrowly implanted NVs. We place them onto a magnetic sample. Then we ramp, for example, magnetic field. We can select these frequency branches. And now we should also imagine that if we put this on a magnetic field, we would have somewhere down here the dispersion relation of our ferromagnetic resonance. And this has actually been pioneered, I guess, in Jacobi's group, and has been continued by others. I take this paper from Van der Saal's group. They do exactly this. So you have here your magnetic material, a strip line that excites spin waves. You place a diamond chip on top with shallow implanted NVs, but many, so we don't really care about resolving individual ones. And this whole thing, because you do it in air, you just stick it on, you have a distance of, let's say, somewhere between half a micron and a micron, which limits the resolution, of course. And then you just detect optically the magnetic resonance. Here you can see the spin wave chip, if you want, from above. So Here we have the YIG, yttrium ion garnet. It's a low damping magnetic insulator. And you have a strip line that excites the spin waves. You place the diamond chip on top, and then you see what you can get. And what is plotted here is the spin wave dispersion that I showed previously. So you have this strange behavior at low k vectors, because here you're in the dipole interaction regime where the anisotropy of the dipole interaction plays a role. And then later on it needs to be quadratic, as you know from your textbook magnetism dispersion. And here these cuts are the omega plus and omega minus frequency that I just mentioned, and these you can see here. So these are these two. So this configuration actually corresponds to this magnetic field. So here's the ferromagnetic resonance of the YIG. You can see it's resonant here. It increases with magnetic field. And if you go to this magnetic field, it intersects this omega minus. And this is exactly this point here. So here the FMR, which is decay equal to 0 mode, is at the same frequency as your omega minus. So you're resonant with this excitation. This excitation is, however, rather boring because it's decay equal to 0 mode, so all spins precess in unison. There is no spin wave. But anywhere in between here, you also excite spin waves. And what we really don't understand is which spin waves do we excite and which spin waves actually carry the information to this branch here, because this is where we detect. And I think there are a lot of open questions here. Nevertheless, you can now image these spin waves, but now you have this precessing magnetic field, so either you do a time-resolved magnetic resonance experiment, that's a bit hard, or you do a trick, and this was actually pioneered in Jacobi's group. You can superimpose a homogeneous driving field at the same frequency. Then, if you compute this, you get regions where you have standing waves, and these standing waves you can image with the NV. So this is a very nice trick, and you can see this here. So this is our chip. It's connected to some coplanar waveguide. So it's in our case, it's a little bit thinner. We apply 2.5 gigahertz, and if we have these additional microwaves on, we can see nice oscillations in the signal as a function of distance traveling away from the strip line. If you turn them off, it's gone. And if you take such a comparison image between on and off, then you can actually see that you image the spin waves. And one nice thing is you can actually image also below contacts because you're very sensitive. Actually, you can do this with Kerr microscopy as well. So here you can see these are big contacts. You can see the spin waves very nicely underneath the contacts also if you tune your material properties correctly. Okay. That's what I mentioned. So we don't really know what exactly happens at all times. So typically you see some selected images, but we see that we excite all kinds of spin waves, and it's not absolutely clear which ones are the ones that contribute to our detection. So currently we're actually building up a combined microscope where we have time-resolved Kerr microscopy plus NV center microscopy to be able to distinguish some of these excitations. Okay, with this I'm at the end. So what is to do? Well, we need high resolution. That's a bit tricky. There are some approaches doing multicolored charge depletion microscopy, and we actually started doing this, so we shine in some donut-shaped beams and some excitation beams to quench the excitation in some regions, but this will for sure not give us a larger signal than just illuminating with red and green. Then we have to take care of this problem. As I said, the distance between NV and sample is of the order of a micron or so. So one needs to make integrated samples and get much closer to the magnetic structures. And what we're working on, and this is one example here, you can see a strip line here, now time in this direction and distance in this direction. We're working on shaping these spin waves beams now that we can send out. And you can see here at about 60 micron, we still have a considerable amplitude, and now we need to reverse engineer, essentially send out this guy and get this amplitude at 60 micron resolution, which is actually rather trivial. And with this, I would like to thank you for your attention and also mention that we have some PhD positions. And hopefully, if this our joint NV proposal goes through, there will be more in the field of NV center microscopy. Thank you very much.
Thanks very much. I think we have time for a few short questions again.
So for your time-resolved NV measurements, how would you go there? You would steer your spin wave to one point and then measure some AC sequence, or what would be the
Yes,
protocol?
then so it's a different experiment, right? So the idea is we will use a time-resolved Kerr microscope to understand where our spin wave pulse goes to. So we steer it to this position, and then we just use point detection for the NV on this position. Yes, so it has nothing to do with spin wave imaging. This is really addressing one single NV center at one point.
And there you want what kind of resolution then to resolve like the interface effects of the Hall effect or something like that?
No, this would actually, this is something that is going in a different direction. This where we would just try to see if we can address single NVs at large distances. This has nothing to do with the magnetic, with the spin wave part.
Okay.
We just use the spin waves to address single NVs at far distances.
More questions. There's a question in the back.
So, hi. This is one of the things that has sort of struck me in the last couple of talks, including yours, that somehow one of the most interesting things in magnetism is, of course, to be able to apply a field and see field dependencies. And yet your sensor has an inherent field dependence. How do you disentangle these two?
Yeah. So this is also a question that Christian asked. Why is everybody using YIG? And the reason why we use YIG, it's because the dispersion relation of YIG is below these excitations, right? If it's above, if you're in a, let's say, more interesting material, then you have some problems. And we don't really know which spin waves actually reach the NV, right? So this is something that is actually totally unclear to me. Maybe there are some people that have some ideas, because you actually generate spin waves all over the place, right? As soon as your frequency, your spin wave manifold is shifted up high enough. And then one should probably also say that people put a lot of power into these chips to get contrast, which means that for a magnetic material like YIG, which has low damping, you have all kinds of nonlinear processes that take place. So you have, I don't know, 3 magnon confluences, 4 magnon scattering, and so forth. So it's not clear to me what you actually see with the NV. And I think this is something that one should really look into. I mean, so far, people have basically reproduced what we know already from standard magnetic resonance experiments, and now we need to understand what we actually see. And people also started commenting on these 3 magnon processes and so forth. So it's actually quite tricky. It's also tricky to change material, I must say.
Okay, one last question, and then I think it's almost time for lunch.
So thank you, Christian, for this nice talk. You mentioned at the beginning, of course, your spin wave equations, they also contain some damping. But then later in your talk, you didn't come back to you. So I assume maybe if you go in one of those resonating channels, that maybe you can characterize this as well. How would
Yes.
work?
So that's also the reason why we use YIG, because this is the material with the lowest damping in the universe so far, at least. There are some other materials that would work at very low temperatures, but this is the one where we know that spin waves travel over millimeter distances. Now, to determine damping, you can do various things. You can just measure standard FMR and look at the Gilbert line width, or you can just take a standard strip line and measure the decay over long distances. But this we know, so we can put a damping in here, and we know it's, in this case, it's about 10 to the minus 4, so it's very small, and that's why you see them bouncing back and forth.
Okay, thank you.